we're going to work with the first problem first because this is the mainly important problem. It's sort of comprehensive. And I want to consider an example that pretty much similar to this one, same amount, not amount of, but same similar task, different conditions, but you should get clear understanding about how the whole thing works. So interrupt me anytime when you have questions, and I will be happy to answer them. So the assignment that I gave you requires you to develop a finite state machine that is actually a gray code counter, and it has 4 states. So pretty much it needs to count them in either direction, either increasing or decreasing direction. And we have 2 commands, increment and decrement, which correspondingly move a state of the finite state machine either one state up or one state down. Reset always moves the state of finite state machine to initial state, which is 0. And we assume that the clock signal that actually drives that finite state machine is very fast. So in other words, any change, any input a user makes is going to be picked up not immediately, but in a very short amount of time when a new rising edge of a clock signal comes in. So for example, if this is our clock signal, let me see if you guys say, if this is our clock signal, and for example, this is the way how user changes some input value. For example, one of the switches that control increment command. So here increment is equal to 0, here increment is equal to 1. And this change will not be picked up by the circuit at this time moment. It will be picked up only here. And in other words, we want to consider that signal as changes to the state of the finite state only as it appears in form of that pulse rather than this pulse. So here is the same situation. It was high, and then it went down, but this change of the signal level is not going to affect state of the finite state machine unless we see the next rising edge of the clock cycle. And only when the rising edge clock cycle of the clock cycle is seen, we're going to make the transition. Actually, we want to read what is the value of the input signal, and we want to copy it to the output. That's just a small remark about the synchronous logic and the way how it works, because it's very important as we're going to develop pretty much a small computer, a computer that can count. We never we usually do not consider computer as doing very simple operation, but in fact it is a computer. And the faster the clock signal, the faster operations it can perform. So let me consider a task of building up a finite state machine that also will have 4 steps or 4 states. But instead of just counting from one to another, I will be just considering quite similar but different task. Let me say I have a finite state machine with 4 states. And those states are A, B, C, and D. And we can transit from any given state to any other one by means of the following command. We can traverse clockwise direction or counterclockwise direction. Clockwise direction or counterclockwise direction. Clockwise direction or counter. And we also can, yes, that's what I want to say. And we also can transit diagonal or across or opposite, let me call it OP for the opposite direction. And opposite is the same, doesn't matter which state we were.
That's right there, that map right there shows all possibilities.
Yeah, that's pretty much all the possibilities. And as I said, from any state now we can transit to any other state. So there is no reset, there is no initial state. Actually, we can choose what state will be initial, but it's not that important. As long as we are given with clockwise and counterclockwise. And let us say we want to light up some LED indicator, or we want to generate positive output if we are in state D or B. So this will be our active output if we are in either of these two states. So what we have here are three explicit commands, which are clockwise, counterclockwise, and opposite. So three input command. In fact, we actually need to talk about four input signals. One of these input commands or lack of any one of them. And for convenient purposes, to make our circuit being as close as possible to reality, we want to consider that each of these input commands are generated by means of some electrical circuit. And electrical circuit is very important to consider because it can make functionality of the finite state machine different. So let me say that we have some voltage source. Let me call it VCC. And then I have a push button or a switch. Let me just call it a switch. And then the ground level. You probably can say that you have no idea about electrical circuits, but it's not actually a real electrical circuit. That's just a concept. And we're going to read a signal from this point. So this will be our signal, and it can be either of these CCW, CW, or OP. All three are implemented in the same way. And then we say that this signal comes into our digital circuit. Digital circuit, for example, this will be CW. And digital circuit is going to have clock generator. And it's going to have the output. So two more inputs we have with the same schematic. Clock generator is also here. It drives the entire digital circuit, which is actually implementation of our finite state machine. And then the output, let me just draw it as some indicator, some lamp. or whatsoever that can light up. And we agree that this indicator will light up if value of the if state of the finite state machine is either B or D. How does this switch work? If switch is open, open means not closed, what will be the voltage here? The voltage here will not be sourced by the voltage source, because voltage source is disconnected from this point. And at this point, the only voltage we have is zero level. So in other words, when switch is open, our signal will be 0. When switch is closed, then we may say that this point is now driven with a voltage and 0 level. In fact, it is driven with the voltage, and here we'll have the high level, just because this resistor will drop the voltage. So in other words, if you consider voltages at or potentials on different sides of the resistor, here it is 0, here is VCC. And this is called voltage drop. Resistor is made for that purpose. There will be a current through the resistor, and that current will create a voltage drop. So here will be 0, here will be VCC. And VCC will go here. So clockwise command will be read as high. So in other words, we're just talking about to make our input either high or low. And now what is important? We should think actually ahead of time how we're going to operate our circuit. When we move it from one state to another, and we release our hand and it stays in the same state. Or which we can hold. As long as we hold the push button, it reaches the same value, the same high value. As soon as we release the hand, actually changes to the open state. Our circuit design does not depend on how we implement that push button, that switch. But let me just, for the purpose of to be more specific, let me just call this switch a push button. Push button which we can press and hold. As soon as we release the hand, it goes back to the open state. In this case, we will have 3 push buttons and we can press any one of them. Now, what will happen if we press one of these push buttons, for example, clockwise, and then we hold it at the same time we press counterclockwise? From this standpoint, it is up to us how to implement that logic. We, for example, can implement the logic in such a way that press to the first press to the first push button will change the state of the circuit. And if while you hold this push button, if you press another one, this second event will be ignored. This is more logical behavior rather than to come up with some strange logic. Because what will be the command if we press 2 push buttons at the same time? In other words, what should we do if we give clockwise and counterclockwise command at the same time? I would even say that in this case we want to consider the fourth input command, which is null operation. But null operation is not actually the physical input. Null operation is input command. And null operation should be considered in any of these states. So in other words, null special command which we can give to the finite state machine. And we can give it in various different ways. One of them is multiple push buttons at the same time. What will be another way to give NOP command. It's push button press will generate no operation command. In other words, if none of these push buttons will be generated, because we should not consider any input to the circuit if none of these push buttons is pressed. So, or at the same time will generate no operation. If we're talking only about one push button pressed, 3 remaining commands will be generated. That's our input logic. And the out, yes?
So the no operation, that's kind of like default.
That's default.
Default.
But default, kind of extended default, because default usually it's what, so in other words, if we do not press, this is the clear default concept. We are in default input state. But when we press more than one at the same time, it's the same result, but it's not kind of standard understanding of default operation. But no operation is just yet another command that we want to handle. Because if we do not handle no operation command, we somehow want to handle situations when 2 push buttons are pressed. That's why we introduce that no operation. And actually, this will be the main source of optimization of our circuit. Because without no operation, our final logical expression for excitation function for triggers will be long enough. But with the presence of no operation, we can introduce don't care conditions. That's what you practiced with the second assignment. This is where don't care condition come from. When we press more than one push buttons, it creates don't care condition. And it is don't care because we do not change anything. That's why it is don't care. We don't care if more than one push buttons have been pressed. So let me try to create a capture on this. All right. Probably I made the capture. Hopefully. And I'm going to erase this, because now I want to talk about encoding scheme for input commands. Any questions? Anything? All right, now we have 3 input commands. Actually, 3 input physical signals that come from 3 push buttons. And they go to some logic which we usually call encoder. And this is input encoder. Because also there could be output encoder. And the using input encoder is to compress the data. Actually, it is to encode the data, but the main goal is to compress the data. What's the point of compression?
Make it travel faster.
That's good point, but also to minimize complexity of the circuit. Here we have 3 wires, and 3 wires can be expressed in 2 wires with the same logic. Why is this? Because here we're pretty much talking about only 4 different states. None of them is active, or one of them is active at any given time. These are the 4 states which we are interested in. We are not interested in having 0, 1, 1. We don't need it. But 0, 0, 1, or 0, 1, 0, or 1, 0, 0, or 0, 0, 0. The 4 possible states, the 4 possible combinations, is what we want. 4 possible combinations can be encoded with 2 bits. So this will be 2 bits that represent our encoding scheme. And let me call, first of all, this is clockwise, counterclockwise, and OP. And here I will have U0, U1. So this will be our input bits. And I can barely hear you.
What is OP?
U1, U0, and U1.
No, OP.
OP, it's when we transit from, for example, B to D, or from C to A.
Oh, okay.
So how do we derive the logical expression here, or in other words, a circuitry in this encoder to generate U0 based upon the 3? So what we need to do is to draw a truth table. Truth table which will show us our intent about assigning particular bits here as response to a combination, certain combination of the input commands. So what we want to do, we want to draw a table of columns. And 5 columns. 1, 2, 3, 4, 5. And I will call them CW. Draw a bit this way. It will be CW, CCW, OP. So these are our U0. Actually, let me write U1 first. And U0 second. And I will say that my U1 is the most significant bit. And U0 is least significant bit. Because later on we can think of combination of these two bits as forming a number. So that number will be in the range from 0 to 3. When we're talking about conversion bits to number, we want to know which one of these bits is least significant one and which one is the most significant one. So bit with the highest index will be most significant bit. And now let us try to fill this table with data. First of all, we want to come up with all possible combinations of input data. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So 8 possible combinations because we have 3 bits and 2 to the power of 3 is 8. And also I want to include in this table the last column which I call command. Command which I'm going to consider as the logical meaning of certain combination. Previously we were talking about physical inputs, physical signals. And now I'm going to talk about command which actually going to affect state of the finite state machine. Because those do not directly affect, but command will affect. So command will be actually mimic of these 3 plus no operation. One of these rows will receive CW. One of these rows will receive CCW command. One of these rows will receive OP. And several rows will receive no operation command. So we know that no operation is, let me just, 0, 0, 1. Clearly that this is the command corresponding to operation high, opposed high. Opposed high means OP command. CCW. What should we do with 0, 1, 1? 0, 1, 1 should not affect the circuit state. So 0, 1, 1 will be no operation. 1, 0, 0 will be clockwise. 1, 0, 1 will be no operation. 1, 1, 0 will be no operation. and 1, 1, 1 will be no operation. So we just named all possible combinations with respect to the logic which we want to implement. And commands are actually ones which you saw on the diagram. And now what we want to do is to come up with combinations to encode these commands. And it's up to us how we do it. So let me say my no operation will be encoded with 0, 0. Let me say my I want to keep the same order as here. So CW will be 0, 1. It's up to us how to assign the numbers, but you see, CW is the first order. So I already have taken 0, 0. So CW then will be CCW, and then will be OP, 1, 1. So if you rank these four numbers, these four binary numbers, there will be no operation on first position, then CW as representation of 1, then CCW as representation of 2, and then OP as representation of 3. In other words, 1, 2, 3. It's up to you how you encode it. Right, so what is important is that first of all you want to keep consistency. For example, this nope, it needs to be 0, 0. But the rest is up to you. So 0, 0 here. And actually there is one observation which I use, actually one idea which I use without explaining you yet. The no operation command is the one which is most frequently used. And encoding it with 0, 0 looks like a good idea just because we want to stay with the minimal energy in the state which is most likely to happen. So think of the state of our finite state machine. It mainly will be driven with no operation command. But no operation command is encoded with 0, 0. 0 is less voltage to be generated. So this is just an energetic perspective to the problem. But there are a couple more design patterns that is actually good to be associated with the less value with the most frequently used command. And you will see it very soon when we will be optimizing the circuit.
How do you associate the no operation?
No operation, we know that
At the bottom.
here,
Like all of those are 0.
because this is the command where we have all three push buttons pressed.
Oh.
All three push buttons should not result in any change.
It's going to be default, right?
Yeah, that's our default. But when only one push button, for instance, clockwise is pressed, that's clockwise command. So that's our table, and now we want to optimize it. Actually, we do not optimize the input encoder truth table, but we later on going to use those no separations to optimize the excitation function for triggers. So what we are missing now is how this particular signal will be driven with respect to these three inputs. So in other words, we're interested in logic. And we can think of the logic as just by evaluating the truth table. For example, U1 is equal to 1 here and here. And that's just what you read in the book. The way how we write this down will be clockwise, counterclockwise, OP. And the first two terms go with zeros. So they go with inversion. Plus that one, there is 1, so this is 0, 1, 0. Clockwise with inversion, counterclockwise, and then OP with inversion. So this expression that needs to be implemented here to generate output U1 of this block based on the signals available here. And similar approach we can implement with U0. U0 will be equal to 1 here and here. So in other words, the first will be 0, 0, 1, same as here, CW inversion, CCW inversion, OP without inversion. And the second one will appear with 1, 0, 0. CW, CW, CCW, and OP. And it will be 1, 0, 0, so 0 will go here and here.
Can you explain that one more time? How you got the U1?
So you identify bits with 1. Actually, rows of the tables with 1. And for each of these rows, you look at combination of the input signals. So for example, that one is associated with 0, 0, 1. That's what we encode. We keep the same order, CW, CCW, OP. CW, CCW, OP. And then we say 0, 0, 1. Inversion, inversion, no inversion.
Oh yeah, but every 0 is inverted. It's
Right.
inverted for every 0.
And same as here. Inversion, no inversion, inversion. Inversion, no inversion, inversion. And same we do for U0. Yes.
For the U0, I can't really see what's after the CW.
After. All right. So the first term is the same as here because they both have 1 in the same position. So this is CW inversion, CCW inversion, OP without inversion. But the second term is that one, which is 1, 0, 0. The first term comes without inversion to correspond to 1, and then the other two comes with inversion. So CCW comes with inversion, OP comes with inversion.
Alright, so there's a 0. So with the 1 is without inversion. So with the 0 is the,
Right. So
it's without inversion, so with the 0 is inversion. For the chart.
I can. Highlight this region and say that one is 1, it goes no, and the two zeros go with inversion. That's the point.
Alright.
So, for example, U1, the result for U1, you only took the result of the ones that were not inverted. You took the ones within the column.
But think of how it will work. Let us say this is our implementation. And then we want to fit any one of these combinations. And we look for only specific combination for the entire equation to be equal to 1. Entire equation, say for U1, will be equal to 1 only if either of these two equal to 1 or both equal to 1. When this term will be equal to 1. This particular term will be equal to 1 with the combination 0, 0, 1, when 0, 0, and 1. When this term will be equal to 1, it's this combination. It is 0, 1, 0. So that's how we implement on all other combinations. For example, 0, 1, 1. this term will be 0, this term will be 0. So that's why we automatically get 1 here, or get 0 here.
That's for the one you circled in red. That's for the U0 though, right?
Yeah, that's for U0. That's the example.
You just worry about the ones that won't change and not the inverted.
Right.
Yeah, okay.
So that one is not inverted, but these two are inverted. And what is important, really important, the order. We want to write this. We want to use the same order, clockwise, counterclockwise, and opposite. Same here, clockwise, counterclockwise, and opposite. All right, let me make another shot here. Capture. I want to capture the screen, not myself. All right. So that's how it is. The only problem we still have with input encoding is the following problem. And I probably need some place to continue drawing, and I later on will need this information. So let me erase that part. And I want to explain the problem that we have now. So the lead, clockwise or counterclockwise or OP, comes from the push button. That's what we started from. VCC. And that's our push button. And the resistor, 0 level. And then it goes to the electrical circuit. So eventually it goes through encoder, and then it comes to the input of a trigger. We want to use D triggers, which are going to be fed with clock signal. And just a couple moments ago I showed you the way how D trigger works. So this is output. This is ENC, encoder. So the one that we worked here. It will also have 3 more input and actually two outputs, but the one of the outputs we just consider as to explain the problem. And then there will be another trigger also fed with the same clock signal but with different input. And we'll have another output. But what is important is that those two inputs, those two signals which are output of our encoder, will stay high as long as push button will be pressed. Right? So, in other words, we press the push button, we generate high logic level here, and for example, this will be the high logic only on the clockwise, on the CW command. And let us say the other two will be zeros. So it will be 1, 0, 0 combination. This is VCC. This is drawing for the push button. I go so fast? All right. CW, all right, the combination.
At the top, like, what does that say?
VCC?
Go to the right.
Here?
Yes, what is that?
COK, clock.
Okay.
That's our meander. So the combination which we're going to generate while pushing the CW push button will be 1, 0, 0. According to our table, encoding table, combination 1 in value for U1 and value of 1 for U0. Right? But these two, 0 and 1, will stay in this state for as long as we keep pushing the button. Keep pressing the button. What this will result? There will be many clock signals come in while we continue pressing the push button. In other words, let us say our state before we press the push button was A. That combination 0, 1 results in CW command. With the very first rising edge of the clock signal, state will change to B. With the next one, state will change to C. Here, state will change to D. And here it will change to A again. The clock signal is very fast. In the assignment statement I told you about like 1,000 pulses per second. How many clock cycles will fit into the period of the push button press? Say we push, even if we try to push and release the push button very fast, still there will be, I don't know, 10, 20, 100 clock cycles. Our intent is to press the push button, release the push button, and make the state of the finite state machine to change only from A to B. In fact, while we press and hold just for a very short amount of time and then release it, there will be many clock cycles and there will be many transitions of the state of finite state machine.
Is that a second switch between the encoder and the first? The 0 right in between?
All right, let me make it more detailed. So our encoder generates U1 and U0. All right, and if input combination is 1, 0, 0, one combination of signal U1 and U0 will be 0. All right, and then these two signals actually will go to some other circuit which we're going to design. It is called excitation function. It will have enough signals. Actually, it will have two more. U0 equal to 1. So two more signals will come from here, and then there will be two triggers. 1 and 2. And the outputs of the triggers actually will go back to that circuit. So this is D trigger 1, this is D trigger 2, and both have that clock signal. CLK. That's the real circuit. Whatever input we generate are going to be fed with the excitation function logic, which has two more inputs, which are actually outputs of the triggers. And then the 4-input circuit will generate two outputs to drive the inputs signals of those two triggers. And the problem is that this combination 0, 1 will stay at the input of excitation function as long as we continue pressing the push button. During this amount of time, many clock cycles will come in, which will make the change in the state of these two triggers to move, to actually respond to command CW. So again, the problem is, our intent is to press push button and release it to make just one transition. In fact, there will be multiple. From A to B, from B to C to D. Every one of these transitions will be made with respect to CW command.
That's in correlation with what you that's in correlation with the counterclockwise and the clockwise, kind of like you just the first diagram you drew for us with the clockwise, the counterclockwise, the opposite. You took that and basically that switches. It gives you all the options.
Right. So this from the 4 states A, B, C, D are actually different of these two triggers. So a trigger is a memory element. It has 1 bit of data. It can store 1 bit of data. Any output of the trigger can be in either of the states, 0 or 1. With 2 triggers, we have 2 bits of data to store. And 2 bits of data is enough to represent 4 states of our finite state machine. That's what we want to do when we will be discussing excitation function. But the point is, the 2 bits which we memorize in the trigger represent the state of the finite state machine. And that state will continue to change for as long as we press and hold the push button. We pressed it, we hold it, and then combination here is 0, 1. That combination here will result in certain command here. So our triggers will move from one state to another. From state A to state B, from state B to state C, from state C to state D, and then again from D to A with respect to the very first diagram. But we still continue giving the CW command. CW command will move from A to B, from B to C, from C to D, from D to A, and again from A to B, from B to C, the clockwise direction.
So there's no set initiation point?
Initiation point is whatever state of these 2 triggers will be when we turn on the power. For example, this trigger, after turning on the power, may be in state 1. This one can wake up in state 0. In this case, combination will be 1, 0. Right? What is combination 1, 0 with respect to our labels for the finite state machine A, B, C, and D? We don't know. We did not yet discuss it. That's up to us to assign certain combination of 2 bits to a certain name. It is actually not important for the design purposes. We can say combination assigned to state A. Or we can say combination 1, 0 is assigned to state D. As long as operation of this finite state machine is purely symmetrical, we just go around the circle either one direction or another direction or across. It doesn't matter how we encode the states. So what I'm saying is that we are missing one state. We correct here. I'm sorry, what? Here. This is what will make say this was the command in U0. So that is U0. For example, U1 was always 1. So U1 equal to 1 all the time. But U0 we put high for certain amount of time. What will be this amount of time? This amount of time will be the same as for how long we continue pressing and holding the push button. So we generated U0 and U1. And if we consider the clock signal, CLK, clock signal will have transitions. That is our clock signal. What we want to do, we want to change the way how U0 and U1 are represented. So in other words, at these 2 points of the excitation function circuit, we want to fit not these 2 long signals, but 2 signals that look like this. It's going to be 0 for as long as the next rising edge. Then it will be 1, but it will stay 1 only for 1 clock cycle. And wait, U1 is 0, right? U1 is 0. And U1 will remain all this. Of course, this is what we are given with, and this is what we want it to look like. What we want for signals U1 and U0 is that doesn't matter how long we continue pressing push button, it generates very short pulse, which is associated with only one transition of. So in other words, we pushed, we pressed the push button, we hold, it generates a long pulse here. But that long pulse needs to be translated into a short pulse, because short pulse with the length of only 1 clock cycle will make only one single transition of these 2 triggers. Say if we were in state B, we'll just move to state C and we'll stay in state C, regardless to how long we keep pressing the push button.
And once the button is released, it's going to stay.
We stay in state C.
It's going to stay in state C.
Right. Otherwise, if we do not implement this, for as long as we continue pressing this, state will change. And think of what will happen. Depending how long, depending how many clock cycles will fit, we can be in any of these states, just because there were so many changes, so many transitions. And now is the question, how can we translate these 2 signals into these 2? That's actually a special block, a special logic that needs to be implemented. That logical block will have 2 inputs and will have 2 outputs. And let me call those 2 outputs as U0 star and U1 star. And the logic behind creating these 2 signals is purely dependent on the state, or actually on input signals which we are given at that side of the logical circuit. In other words, if you want to translate the long signal into a short one, the long into a short pulse, you want to look what was the long pulse. And now see, try to this signal will be this. We will see what in any given clock cycle. Let me keep important parts, and I'm going to erase the rest. What do I need is, I probably can erase now because I want to explain this clearly. Let me erase. So this, and I'm now going to explain how we can implement this concept. For the implementation purposes, we can independently consider any one of these, U1 or U0. So let us be specific and consider only U1. Because U0 star will be composed, will be developed, will be built with the same logic. And what we do, we say that this is our clock cycle. Let us draw it long. This is our clock cycle. Let us say this is our U0. And let us try to consider that block that has U0, U1 as inputs and U0 star and U1 star as output, as having the following logic. Inside that block, we want to have another pair of triggers. So what I'm going to draw here is what we have inside that block. But I will draw it only for one channel, for U0 channel. Same logic, same circuit will be for U1 channel. So for U0, we want the input into a So in other words, this is U0 and this is U1. Wait. Output state. It's not U1. This is. I'm sorry for that. So that's U0, and we put it immediately to a D trigger, which is fed with clock. So that's our D trigger. And then we take U0 and then output of the D trigger, and then do some logic, and this is our U0 star.
Which one does the clock at the top extend to?
That's the same. We don't need it here.
So the clock only goes input into one, and it goes from there.
Can you repeat? Clock signal, that one is that signal. So we just feed it to, that's how trigger works. It needs not only data input, but clock signal. And with D triggers, what we will have is every time the rising edge of the clock comes in, we're going to read the input signal. So we read our U0. And let me call this signal, this intermediate signal, U0 bar. So U0 bar will have 0, and then it will read the value of the input U0 at the rising edge of the clock. So it is 0, it will remain 0 for the next rising edge of the clock. Here it will read it again, and again 0 till the next one. 0 again, and here it will read it as 1. So it will make the transition. And then it will continue reading it as 1, 1, 1, again 0. So it will stay 1. I don't want to erase it, so I will just draw it above. So that will read it as 0, and transition will be made. So that's our U0 star. And what to implement in this logic is simple rule. If both these two signals, both of the input signals that are fed into that logic, if both of them are 0, so now let me just draw the truth table for that block. We have 1, and we want to implement U0 star. 0, 0, 0, 1, 1, 0, 1, 1. All possible combinations. What should we do when both are zeros? Obviously that when both are zeros there is no pulse. Again, here is here, and now at this time moment, let me be more specific in the way how it works. At this time moment when the rising edge comes in, we make a decision to change state of U0. In other words, U0 bar, it's output of the D trigger. So we make a decision, the schematic in the D trigger decides to change the output to 1. But actual change of the output signal will take place after a very short amount of time. So this is called switching delay. Switching delay. It is a matter of nanoseconds. It is very fast. But this delay is always present. Why this delay is important is that at this time moment, when the rising edge of the clock is present, the combination will be 1, 0. But on the next clock cycle, combination will be 1, 1.
1, 1 wasn't valid because it can't be pushed twice.
No, the push button still remains pressed. This is how long the push button is pressed. Now, let us see what we have. 0, 0, and let us try to draw the diagram for U0 star. When do we want that short pulse to be generated? We want that short pulse to be generated as close to the beginning of the... That's first of all. And that short pulse must be as long as the period of a clock cycle. Obviously that we cannot draw that short pulse, the U0 star, here, because we don't know when this event will happen in the future. We cannot draw it here. So we have to wait until we find out that the long pulse came in. So in other words, our U0 star must remain 0 up to the moment when we read this clock cycle. And this clock cycle is a unique situation. This is the only time when we have combination 1, 0. Look what is happening. Combination 0, 0. For only one clock cycle, combination will be 1, 0. Then for many clock cycles, combination will be 1, 1. And then when we're going to release the signal, combination will be 0, 1. Well, also for one clock cycle. And then 0, 0 again. So in other words, we want to keep it 1, we want to keep it 0 for all combinations except 1, 0. And by design, we know that that combination will be present only during one clock cycle. In other words, here we want to raise it, and it will be good only for one clock cycle. The only question left is how we implement that logic in that block. And this is very straightforward. The combination which is associated with output 1, 1, 0. Again, combination of 1, the output is, and that combination can be read as U0 star equal to U0 bar inversion. So this is not inversion of U0, this is U0 bar. Probably it's not the best notation. Let's tilde it, not to mess up with bars, with inversion. So this is tilde, and this is tilde, and tilde here as well, and tilde here as well. So in other words, we want to keep this block, I want it to be blue. We want to keep this block, which is fed with U0 and generates U0 star. So instead of letting U0 to go to the finite state machine, we allow U0 star to go to the input of finite state machine, to the excitation function. And this guarantees that anytime we press the push button and we hold it, it doesn't matter how long we hold it. There will be only one single transition because U0 will be active for only one clock cycle. And same with U1. That's actually the trick that makes implementation of finite state machine more robust. There are a number of tricks, and it's not actually part of the material. And if you do not implement this, assuming that you never had a chance to read about this in some other sources, I wasn't going to judge you for the lack of this technique. But I'm explaining this because in the next course, the computer architecture course, we will continue with digital circuits. And this technique is used a lot in there. I just want you to become kind of introduced to some tricks. All right. On this, if I'm doing this right. And I'm going to the only thing I need to put in place is equation for my U0 and U1. And actually you have the notes on that. What we're going to do now is finite state, the logic that drives the triggers. Here again the circuit. That was our 2D triggers. And let me say the first one generates state S1. Both of them are fed with the clock signal. And input here and input here is generated by some logic which we call excitation function. Excitation function. That excitation function is fed in turn with U0 star and U1 star, and also with the previous state of both triggers. And let me say S1, so how can I call this? Let me call it F1, F2. F1, S1 is 0, F1, F0. So this is what we're going to work at the moment. And I want you to clearly understand the function of D triggers here. D trigger, in other words, it's called delay trigger. It gets certain state of the output with respect to state of the input when new rising edge of the clock comes in. So in other words, it reads the input data and it writes when the clock rising edge comes in. It makes the delay until after the rising edge is here. So that's why we call S0 the previous. F0 will be something that will change the state, but change will take only when the clock will come. Now, we want to develop that excitation function, and that excitation function, and it looks like S1, S0, and it needs to generate two. Let me use the same notation, the same order, when the first most significant bit goes first. So pretty much this is yet another logical circuit that needs to be developed. And this time we will be optimizing this logical circuit. So it has 4 inputs, 2 outputs, and we want to draw the truth table. So our truth table now will have 16 rows. U1 star, U0 star, S1, S2, and the outputs will be F1, F2. So that's the bold line is to separate inputs from outputs. On the input side, we just list all possible combinations. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, and let us now split this table into 4 pieces. That's the logical split. Right here. And we make that split by looking at possible combinations of U1 and U2. In the first group of rows, combinations is always 0, 0. On the second group, it is always 0, 1, 0, 1. On the third, it is always 1, 0, and on the fourth, it is 1, 1. What is a combination? A combination responds to a command. And help me with these combinations. What was? I think it was no, right? We just discussed it a couple moments ago. Clockwise, and then 0, 1, 0 it is counterclockwise, and then 1, 1 it's opposite. So these are the commands. What do we have as the third and fourth column? These are possible combinations which represent current state of the finite state machine. So far we're only talking about states in form of A, B, C, D. So now we want to make assignment. Let me call, so this is U1, U0, and this is what we use for input encoding. For the state encoding we say S1, S0, and 4 combinations are 0, 0, 0, 1, 1, 0, 1, 1. And now we just want to name them. Let us just name them in the order. But again, it is not important how we assign combinations of bits to particular state. As long as we list all states A, B, C, D, we are good. We can list, for example, those states as C, B, D, A. But it probably doesn't make much sense unless we have a reason for that. So we list 0, 0 to be A, 0, 1 to be B, 1, 0 to be C, 1, 1 to be D. And now we want to write something down here. And the logic is straightforward. Let us see. The state was 0, 0. 0, 0. Combination is, the input is 0, 0. We know combination 0, 0 from the input is no operation. Applied to the state 0, 0 result in new state 0, 0. This makes us the new state equal to 0, 1. 1, 0, 1, 0. So we this from here because that this combination of U1 is a operation. The second cell is a bit more tricky. Clockwise command given to state 0, 0, to state A, according to original diagram, must result in new state equal to B. So from 0, 0 with clockwise, we go to B, which is 0, 1. The next one. From B, we go to C. From C, we go to D. And from D, we go to A. Same logic here. Command now is 1, 0, counterclockwise. Counterclockwise moves us from A to D, from B to A, from C to B, and from D to C. And finally, the command is opposite. From A we go to C. From B we go to D. From C we go to A. From D we go to B. So we wrote down what we want that circuit to generate. And this is with respect to our intended behavior, or with respect to intended behavior of the finite state machine. We want it to behave that way. That's why we write it down that way. That's why we put particular 0 and 1 in certain places. So this is the logic of finite state machine. If we wanted, for example, A to go to D with clockwise command, zeros and ones would be different. But we want it to be this way. That's why zeros and ones are. And now the rest is a straightforward task to optimize it. If we do not optimize it, we just say my function f1 will be equal to 1 here, 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 and here. So there are 8 for f1. 8 terms, and each term has 4 variables. So this is long equation with 8 terms, and each term has 4 variables. But this will be the implementation for function f1. You just want to implement it here. In other words, put some logic here to drive f1 based upon the 4 signals. And then the magic will start. We press certain push button. Doesn't matter how we press it, we eventually release it. But at the very beginning of that press, U1 and U0 will be made into a short pulse. Whatever state it was here will be considered with respect to that table, and the new F1 and F0 will make a change in triggers D1 and D2. And the new state S1 and S0 will be recorded in the trigger. And that state will remain here until after we press some other push button. That's how our finite state machine will work. We press push button, we release it, we press another push button, we release it, we do any change. So now let us try to think of how we can optimize it. And you're already familiar with the technique. We just want to draw a Carnot map. One Carnot map for F1, one Carnot map for F2. And on that Carnot map we will be depicting 8 terms for F1 and 8 terms for F2. 1, 2, 3, 4, 5, 6, 7, 8. And the beauty of this approach is that we have don't care conditions. Any one of these rows is a don't care condition. Any one of these rows does not change the state. But let me first draw the and start from F1. It will be 4-variable Carnot map. So 0, 0, 0, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and we'll say that these two bits will be U1, U0 star, and these two bits will be S1, wait, it should be S0, the second one, S0. And now we want to draw the combinations. For example, this, by the way, this will be for F1. So let us put ones in those cells which correspond to that term, which is 0, 0, 1, 0. Actually, let me skip the first block because the first block are all don't care conditions. So in other words, everywhere where we have 0, 0 for these two terms is don't care. It doesn't matter that we have ones in here, 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 and here. It is good for us that any row in this table with the combination 0, 0, it's a don't care condition. We know that this is no operation. It should not affect the state of the finite state machine. That's why we put 0, 0. And that's how we assign the don't cares. Now, with the combination 0, 1, that row will have ones at 0, 1 and 1, 0. 0, 1 and 1, 0. Here. With combination 1, 1, we will have at 0, 0, 0, 1. So 1, 1, 0, 0, 1, 1, 0, 1. And we have ones at 0, 1 and 1. 0, 1, 1. So that's the map for variable F1. And let's draw.
Wait, I think you made a mistake on 1, 0.
Which one?
The bottom row.
It's here. It's this cell.
Would it be 0, 0, 1, 1?
All right, let me check. So that one we have 1, 0, and the 1 is here and here. So combination should be 0, 0 and 1, 1. Yeah, you're right. I think I looked. Wait. Combination will be 1, 1 and 0, 1. So
why would it be 0?
No, you're right. I'm sorry. It's a mess. That's a mess.
0,
So
1, 1.
it will be 0, 0, 1, 1. And 0, 0, 1, 1. Right, thank you. So 1, 1, 0, 0. Do you see any other errors? So with 0, 1 we have it 1, 0, 0, 1. That's correct. And with the last one we have it 0, 0, 0, 1. 0, 0, 0, 1. That looks correct. And let me draw the map for F2. So same 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And now again care condition. And starting this, it will be 0, 0. And that one is 1, 0. For that part, it will be 0, 0 and 1, 0. And for this, it will be 1, 1 and 0, 1. All right. So let us now optimize it. All right, not much can be done with the first map. We probably can do this cluster, and that cluster. And then this cluster, and then this cluster. So 1, 2, 3, 4, 5. 5 clusters for the first map. But for the second map we are lucky. So that will be first. This will be second. That will be third. And this will be fourth. So we can use the corner ones as long as all of them are marked. We can consider them for optimization as well. And now, right, let me make a screenshot. Of this. And I want to erase the truth table because I want a space to write down the result. For F1, we have, all right, let me start with this cluster from the bottom. So here we have U1 not inverted. S1 is 0 inverted. S1 is 0, both inverted. That's for that cluster. Now for this cluster, it will be U1, U0. Not S1. Because for both values, S1 is 0. For this cluster, it will be U0 not inverted and S1 inverted, S0 not inverted. Now for that cluster, we will have U0 inverted and then S1 is not inverted. And the last one is this cluster, which is U1 inverted and S1 as it is, S0 inverted. That's for F1. And for F2 we will have 4 terms. Let me start from this small cluster in the top left corner. So it will be U1 inverted and then S1, S0 both inverted. Plus this cluster, U1, U0 without inversion and S0 without inversion. And then that cluster. Will be U1 inverted and S1, S0 and S0 will be inverted. And then the last the question. So here we have for row 4 it will be U0 inverted and S0 inverted. So these are the 2 logical expressions, and you can see previously we had 8 terms from the truth table, but we ended up after optimization with 5 and 4 terms only. And terms are shorter and number of terms is less. That's how we use don't care conditions. And don't care conditions come from the fact of utilizing no operation input command. So the only thing we are missing now is their output signal. And if I'm not mistaken, my output was going to be equal to high when state is equal to A or C or B or D? B or D? All right, so B or D. And B is what? B is the combination 0, 1 and D is combination 1, 1. Right? So these are the bits assigned to S1 and S0. And now I can say that my output will be equal to this combination S1, S0, and S1 with inversion plus combination D is S1, S0 without inversion. We probably optimize, and I think it will be quite interesting. So we can factor out S0. I don't really want to draw the Carnot map for two variables, but we can, and it will be S1 plus S1 inversion. Is logic 1. Right? So it will be just S0. In other words, our output will be equal to 1 when S0 is equal to 1. That's the output function. Any questions? There is one part left, and this part tells you in what logic I want to see these logical equations to be implemented. So let me make a capture. And now I want to erase this, and we'll show you on the example of, for example, say output. Not output is straightforward. I will show you on the example of F2 how to make it implementable, say in form. I want to keep it written. Say I want to implement this logical equation by using only logic gates which are 2 OR. Let me make it inversion, because without inversion there is nothing I can do. 2 NOR. 2 NOR block, it's nothing more but a logical gate with 2 inputs and 1 output. A, B, C. And the truth table is this. A, B, C, all combinations 0, 0, 0, 1, 1, 0, 1, 1. And the logic of 2 NOR block is opposite to the logic of 2 OR block. 2 OR, it's when we have OR, logical OR operation. Logical OR operation will have 0, 1, 1, 1. With 2 NOR, we inverse this logic. It will be 1, 0, 0, 0. Right? But let us see in this part. First of all, we want, let us just outline inversion where we have 1. Second of all, we want 2 AND. Block that has 2 inputs and AND operation. The fact that each of these is inverted, we can implement by using inverter. 3. We want 3 AND block. And number 4, we want to have 1, 2, 3, 4 OR block. Okay? So pretty much we want to implement 4 operations. For that 4 operations, we have only one basis block, which is 2 NOR. Let us start from inversion. What should we do with this block? Or in other words, assume that you have many blocks of this kind, and you can interconnect them as you want. So here is your input, here is your output, there is A, there is not A, and here you may have many blocks of that kind and can interconnect them in whatever fashion you want. So what will be this interconnection to implement an inverter? That's the task. So that's the question. Let us see what will happen if we the 2 inputs of that block. What will be the truth table? So let us consider this, which we are given with, but we're going to connect the 2 inputs. And in this time we have A, and then some function f at the end. Based on the table, we will have the same value for the first input, the same value for the second input. So 0, meaning that both of these inputs are 0. The output will be 1, right? 0, 0 gives us 1 at the output. When A will be 1, both of them are 1s, output will be 0. So connecting of 2 inputs of that block gives us an inverter. So this is inverter. We're done with step 1, with the first implementation. We just want to use that block and connect 2 inputs. What about, for example, 2 AND? 2 AND is depicted like this. A, B, and then C. And we say C equal to AB. Let us use De Morgan's law and represent AB as not A plus not B inversion. And now we want to say that this is nothing more but use of 2 OR block where each of the inputs is inverted. So in other words, this is my A. I want to put it into inverter. I want to feed my B through inverter, which I already developed. So this is not A, this is not B. And then I just want to feed them through my given NOR block. And this time it will be AB. In the same way, you can implement 3 AND, but you just want to represent C or whatever. Again, use the in other words, name ABC as not A plus not B plus not C Everything is. So for purpose, we want to have inverters and 3 NOR. But what is 3 NOR? 3 NOR is inversion of 3 OR. What is 3 OR? OR is of 2 OR and another 2 OR. In other words, you might think of this block first. So let me call this A, let me call this B. I want to feed their result of their OR to here, and I want to feed C into the second input of the second OR. So this will be A plus B plus C. Right? But I don't have 2 OR yet. I have 2 NOR. 2 OR in this case, it is 2 NOR followed by inverter. So if I want to implement the 2 OR, I want to use my given 2 NOR and then feed it into another 2 NOR with connected inputs. And same here. 2 NOR and so this time it will be A plus B plus C, but only with the use of 2 NOR blocks. Then you just feed, instead of A, B, and C, inverted versions of A, B, and C, and this will be your ABC. I think you've got the point, and unfortunately I have to go. I have a Storm Day meeting at 11. So anybody has any questions? That pretty much covers the first part. Unfortunately, we didn't have a chance to consider the second part of the assignment, but it's way easier than this one.